Hello, everyone, and welcome. So many of you might know that we celebrate Science Day to honor the incredible work of Sir C.V. Raman. Back in 1930, he won the Nobel Prize in Physics for a discovery that was, and honestly still is, a total game changer, the Raman effect. But what is it really? Today, we're going to roll up our sleeves and break down exactly what this effect is, how it works on a quantum level, and why it's such a powerful window into this secret world of molecules. So here's our game plan. We're going to start with a concept you already see every day, light scattering. From there, we'll get into the two main ways that can happen. And once we've got that down, we can really dig into the Raman effect itself, its two different flavors, and finally see how this teeny tiny energy shift gave us one of the most powerful scientific tools we have. All right, first things first. Before we can possibly get the Raman effect, we have to understand the stage where this all plays out, the basic idea of light scattering. At its heart, scattering is really simple. It's just what happens when light hits something and gets bounced off in a different direction. And you're totally familiar with this. I mean, have you ever looked up and wondered why the sky is blue? That's sunlight scattering off of molecules in our atmosphere. Or, why sunsets are so red and orange? Yep, same reason, light scattering. It's happening all around us, all the time. But as we're about to find out, not all scattering is created equal. Okay, this is where things start to get really cool. When a little particle of light, a photon, hits a molecule, that collision can go one of two ways. You can think of it like two billiard balls hitting each other. Sometimes it's a perfect, clean hit where no energy is lost. And, well, sometimes it's not. The vast majority of the time, what we see is something called Rayleigh scattering. This is a perfectly elastic collision. Imagine a super bouncy ball hitting a wall and bouncing off with the exact same speed and energy. That's what happens here. The photon hits the molecule and scatters away with the exact same energy it came in with. No change. This is the normal, expected outcome for pretty much every photon out there. But, and this is the discovery that changed everything, Sir C.V. Raman found the exception. In about 1 out of every 10 million of these collisions, something different happens. The collision is inelastic. The photon hits the molecule, and when it bounces off, its energy has changed. It's either got a little bit more or a little bit less than it started with. And this super rare special event is what we call Raman scattering. So this brings us right to the main idea. This whole phenomenon, this process of light changing its energy after it bumps into a molecule, that, in a nutshell, is the Raman effect. The absolute key here is this exchange of energy. It's like a tiny transaction. The molecule can either steal a bit of the photon's energy, or it can give some of its own energy to the photon. This transfer is what it's all about. So naturally, the next question is, how does that work exactly? Well, this energy swap can go in two different directions, and that leads to the two distinct types of Raman scattering that we see. We call them Stokes and anti-Stokes scattering. Let's look at how this plays out. On the left, we have Stokes scattering. This is when the photon comes in and gives some of its energy to the molecule, kind of bumping the molecule up to a higher energy level. Because the photon lost energy, the light that scatters away has less energy, which means it has a longer wavelength. Now on the right, you've got the opposite, anti-Stokes scattering. This can only happen if the molecule is already excited and has extra energy to spare. In this case, the molecule gives its extra energy to the photon. The molecule calms down and the photon flies off with more energy than it started with, giving it a shorter wavelength. So at this point, you might be thinking, okay, that's kind of neat, but it's a tiny energy shift that almost never happens. Why is this such a big deal? Why a Nobel Prize? Well, it's because that tiny shift contains an incredible amount of information. See, the most important piece of data we get out of all this is something called the Raman shift. We don't just care about the final energy of the photon. What we really care about is the difference, the exact amount of energy that was either gained or lost in that collision. And here is the beautiful central idea. That specific amount of energy a molecule can gain or lose is totally unique to that molecule. It's determined by its atoms, how they're bonded together, how they vibrate. So the Raman shift is essentially a molecular fingerprint. No two different molecules have the exact same one. And once you can read these fingerprints, you can do some amazing things. Scientists can identify an unknown substance just by shining a light on it. They can figure out its exact structure, analyze its chemical bonds, and even watch chemical reactions happen in real time. This idea is the foundation of a technique called Raman spectroscopy, which is a powerhouse tool used every day by chemists, biologists, and engineers to figure out what stuff is made of. So let's just step back for a second and appreciate the scale of this. This discovery wasn't just some curious little quirk of physics. It was like finding a key that unlocked a whole new way of looking at the universe. For finding this subtle, incredibly rare, but hugely powerful effect, Sir C.V. Raman absolutely earned that Nobel Prize. He gave science a way to probe the very fabric of matter using just light, and in doing so, he completely changed chemistry and physics forever. And that kind of leaves us with a pretty inspiring thought, doesn't it? Raman showed us how to translate this hidden language that's spoken between light and molecules. And now that we can read these fingerprints, it just makes you wonder, what other invisible secrets are out there, just waiting for us to find the right way to listen?